Hi everyone, my name is Nikhil. I'm going to present one of the security vulnerability in machine learning models, the way they are deployed. It's called GDALR, an efficient black box duplication attack on machine learning models. So the GDALR is actually a technique that we have developed which efficiently duplicates the black box machine learning models that have been deployed on cloud. We'll get into details of GDALR in a while. So this is a little bit about me and my colleague Rewanth. So I'm a security researcher at Pire2 Software Labs. So Pire2 does the security consulting and research. We also have an in-house fuzzing and testing frameworks. So my job in Pire2 is to implement machine learning in fuzzing methodology, and I also work on testing machine learning applications for different vulnerabilities in machine learning. So you must have heard about adversarial learning. So in adversarial learning, what we do is we give an image to machine learning models and make the model predict it the wrong way. So yeah. So this is the agenda of today. We'll first get an introduction to machine learning, how the machine learning works and how the models are deployed and how users actually get access to these models. And then we'll understand what model stealing attack is and the traditional approach that attackers have been using to steal the models that have been deployed on cloud. Then we'll discuss the inefficiencies in previous attacks and how we countermeasured it to develop a new attack which is called GDALR. Okay. So this is called a perceptron, which is inspired by the neurons in our brain. So the basic idea behind it is if we mathematically model how our brain works, then we can implement it on computers and make computers learn whatever we want it to learn. So here you can see the axes, the x1, x2, x3 are the inputs to our neuron, and there are some weights. So we multiply x with weights and then pass it through an activation function which tells you whether the neuron is activated or not. So that is exactly how our brain works. So there are multiple neurons that are connected, they activate in a pattern, and then we make decisions. Yeah. So this is just one neuron, and you connect multiple neurons to create a neural network. So there are certain inputs that you give to neural network and you get some output. For example, you can give an image, the pixels of image as inputs, and then it will tell you what kind of image it is. So it's called a classification task in machine learning. So there are basically two types of tasks, which is regression and classification. In regression, you basically predict the future, and in classification, you try to classify a given input in certain specified classes. So here's an example how a neural network should work. So this GIF is actually taken from 3 Blue 1 Brown's video. He's a great YouTuber who does videos on mathematics. So if you want to get an intuition behind how neural networks and machine learning works, you can go and check his videos. So here there is an image, handwritten digit image of 3, and the size of image is 28 by 28, which turns out to be 784 pixels in the image. So you can pass those 784 pixels in our input layer of neural network. There are a bunch of weights that are connecting different layers of neural network, and what we want at the output layer is we want the third neuron in the output layer to be activated, this one to be activated, so that we will get to know the image that has been given as input is the 3. So suppose we provide input as 9, then it should activate only the 9th neuron. But since the weights are randomly initialized, so x is our pixel values and weights are randomly initialized, so the neural network will only predict the garbage values. So we don't want these values, we want the activation to be in this way. Okay, so this is the activation that we want. So difference between what we want and what we are getting is called cost function in machine learning terminologies. So our aim is to modify the weights that are here in such a way that the X into weights passed through activation should give you this. So that problem of optimizing weights is called optimization problem, and there are certain algorithms that have been developed to optimize these weights. So what we are seeing here is called backpropagation. So first we pass some image to our neural network, then it will predict some output, and based on the difference, the cost function, the difference between what we want and what we are getting, we change the weights of this neural network. So to change the weights, we have to optimize the weights in such a way that after giving some image, it should only trigger the relevant neuron in the output layer. Okay. So here's the essence of optimization, how optimization works. So there could be millions of weights that we are tweaking in optimization. So optimization is kind of a black, we can say it as a black box, which takes parameters as inputs. The weights are parameters to our optimization problem, and it will optimize some value, which is the cost function. So if the cost function, the value of cost function is minimum, that means the optimizer has actually changed the weights in a way that it is predicting the right output of our class. So here we can see the C is actually the cost function. We are implementing partial differentiation, so you don't have to worry what the partial differentiation is. So this actually tells how the cost is different from what we want it to be. And this is alpha, which is also called learning rate in machine learning terminologies. So this alpha determines how abruptly, how intensely we change the weights of our machine learning model. And this equation is run into multiple epochs to change the weights. So after every epoch, the weights are changed, and it learns how to predict, how to actually predict and classify the input image to certain number of classes. So in this image, you can see that there are X and Y are the parameters, and Z axis actually determines the cost function. So after every iteration, you can see the value is minimizing, and initially the neural network was here, and it goes down here because of the optimization algorithm that we have implemented here. So the neural, this is what tells you that the neural network is being trained efficiently. So after training, this is what you get. So you pass in some input to our neural network, and then it will activate the relevant neuron in the output layer. Yeah. So this is the basics of how a classification task works on neural networks. So the input image could be anything, like we can make the neural network learn how to classify an image of orange and apple. So this is another type of neural network called convolutional neural network. So previously what we have seen was multi-layer perceptron. So convolutional neural network was mostly developed to classify images for image classification problem. So you can see that there is a filter of certain size. You don't have to actually worry about the numbers that are there in the filters. So there is some filter of certain size which goes through the image. So these are 3 layers of image, the R, G and B layers of image. So the filter passes through the image and then develops some values using convolution operation. So after those values, so these are flattened out and passed to the normal MLP that we have seen previously. So what this filter learns is, it actually learns the edges and curves that are there in the image. So if you are going to classify a car and bicycle in an image, then you want to learn how the wheels are developed and how the axis is developed in the image of bicycle and car. So they have different types of curves and different types of edges. So the neural network learns those things. These filters actually learn those things and then classify the image. So in convolutional neural networks, the cost function actually, the optimizer actually optimizes the values inside these filters so that the result of our convolution operation in such a way that it actually learns about the parameters that are there in the image. So at the end, this is what we get. We pass some image in input and then we get some activation at the output. So the neural network has learned how to classify an handwritten digit. Okay. So after this learning, these models are deployed with different ways to the user. So a model actually contains the weights of the neural network that has been trained. So companies actually invest a lot of money and user resources to compute the weights of these neural networks. The gradient descent optimization algorithm and other optimization algorithm actually take a lot of resources to actually train the neural networks and get the weights. So these weights are actually we can say it's an intellectual property of that company, and if someone gets access to these weights, then the user might not have to pay to the company that has developed or trained the neural networks. So in model stealing, there are basically two types of attacks. One is online and offline attacks. The way these models are deployed to the user actually determine how we are going to attack the algorithm. Suppose an organization develops a WAF system, so that the model has to develop, so that the model has to deploy it with your exe package. You don't want your WAF to actually send the query to some cloud and then wait for the cloud to classify whether the query is malicious or not. You just want the model to run locally on the systems and classify the queries, right? So in that case, the developers of these models, they don't have any option other than deploying those models to the user's computer. And in online attacks, we can actually the models are actually deployed to a cloud, and then users are given an API access to the cloud, and then users can actually query the APIs and get the predictions from that model. So this is how the offline attacks works. You first reverse engineer the executable and get to know where the model is stored and what size of input the model accepts. Then you locate the trained model on the device. You learn about the model, what APIs have been used to develop that model, and what frameworks have been used to develop it. Then you can actually get to know about the framework and use that model by yourself and make the model work for you. So here's an example we were testing at our company. There's an Android app that actually classifies 1,000 types of images and gives the prediction. So the developers of this app have actually put on some cost on using different types of models. They have different nets called, one is animal net to actually classify the images of animals into different classes. Then there is a cat net and dog net. You get the idea, right? So once we reverse engineer, I have used the JADX tool to get into the code of Android application. Here you can see there's some model folder, and there is a categories file which actually maps the activation from your output layer to the category. So in our example, the third neuron means the third image belongs to handwritten digit 3. So this is what the categories file do. And this model folder has different models and some stat file which has some statistic about the model. And using these models, the Android application was actually predicting what kind of image it is seeing. And you can see that there's an instance of model class, and here's an interesting number that have been passed to that instance. So whenever you want to pass an image to your model, you want to know what size of image the model accepts. So this is the size that our target application was accepting. So every image is converted into 224 by 224 dimension, and then it is passed to the model. So I've analyzed the serialized version of that model that have been stored in the Android application. You can see here that there are some strings like torch and nn.sequential, nn.spatial convolution. You can just Google the strings that you get, and you get to know that there's a framework called PyTorch, which have been used to develop these models that have been deployed on the Android application. So now our task is to get to know about PyTorch and try to load these models and make them do predictions for you. So after reading about how the PyTorch works, so this is the function to actually load the model. You can just provide the model path and it will load the model for you. So your neural network is ready for predictions. Then there is some predict method that we have developed to change the image into 224 by 224 size and passed it to the model and get the output. But we got an error. So it turns out the PyTorch uses legacy package of neural network to develop a layer called a linear layer. So that is what happens when you get into the legacy code. There was no documentation about how the code was working, and there was no documentation about the torch legacy functions. So you can see that the model actually expects dimension of linear layer to be 2, but the linear layer was actually getting the dimension of 1. So we are only getting 128 values from view layer to the linear layer. So there's a function in legacy. Again, you have to do the same steps. There's a function in legacy which converts the shape of that input to a 2-dimensional shape. So there are the same 128 values, but the shape is different. So values are not changed, that just the shape of input is changed. And the model worked. So this is how an offline model stealing attack works. So many microprocessor developers like NVIDIA and Intel are developing their own frameworks to actually transform the models that have been trained using these TensorFlow and PyTorch frameworks to optimize and to be loaded in their processors so that it works faster. So we can again, that will be another layer of security, but we can again load these models and learn about those frameworks to breach that security also. So this is all about offline model stealing. Now Rewanth will give an introduction about machine learning as a service, and we'll talk about online model stealing attacks.
Hello guys. So I'll just give you a minute to process whatever you have heard till now, and then I'll continue with my presentation. Okay, I think 1 minute will be too long, so I'll just continue. So whatever he had said, I'll just give a small recap on the prerequisites which you need in order to understand the further slides. So effectively everything comes down to a model. Model is, in simple algebraic terms, model is just a function, f of x equal to y, which you have studied in your childhood. So f is the model, x is the input, and y is what we get. So right now, every company is turning in these machine learning into their business models. So few of these service providers are Amazon, Google Cloud, and so on. The basic function of all these products is it will just take the input, it will classify it, and it will give you the output. And they charge on per query basis or per hour basis. If you are making n number of queries, your cost function will be n into something. So yeah, for example, this is the, this is what Microsoft does. It is having the cloud, they hosted their service on the cloud platform, and they provided an API which the user can call them. So here are the clients, they just call the API, which in turn makes request to their internal machines, and eventually it will give the output. So what the attackers can do here is they can try to take the deployed model on the cloud and they can try to sell it on the dark web, or they can put it in their own business model, which will eventually lead to loss for the company. They have spent thousands of hours, hundreds of computing power, GPUs, electricity, everything in order to create the best model, and they charge the user accordingly. But once if the attacker is able to get his hands on this particular model, then eventually the company might face some issues. So there was a guy called Tremor. He initially started working on this kind of approach in 2016 to explain how one can steal these machine learning models. So this is kind of complicated image which he has given. We try to simplify it later on. So there will be a black box model on the cloud, and the user will be sending the input. He'll be getting the classifications and so on. It's kind of pretty messy, but it explains pretty much. After he will train his API and he will try to replicate the model. So I just converted it into as much simpler terms, though the image is not impressive, but it will work for the presentation. We have the trained model deployed on the cloud. We have the image over there. The user will just give the input through the API call. He'll get the target class. This is how the machine learning as a service works. So this is how the attack happens. There is the same process. If you see the first image, it's almost the same. Just after the attacker gets the labels from the target class, he will use to train his own model on the cloud. And just for the formatting of the input and output, the input will be a set of array with all the features and everything. And once you pass in the inputs to the cloud, it will predict the probability for the each class. Let's say you're having 3 classes. It will predict in which category the input will fit. It says some X probability might be possible that it belongs to class 1. X 2% of probability might be there. It belongs to class 2 and so on. But in machine learning as a service, in order to make sure they are secure, they won't share you the probability values of each of them. They will just share you the maximum value of to which class the particular input belongs to. So this is just an Excel sheet to explain what I have said so far. So these will be your input values, and the cloud API output will be something like this. This is what the current work going on. They just provide you with these outputs, and this is about machine learning as a service. In this way, you will be given the models and you will be able to classify the input. So there are some inefficiencies with the whatever. So I would just like to add a point. As of now, with the present tech methodology, they will take these cloud API outputs, which they will use to train their models. But there are some inefficiencies with this approach. One of this is, you can see the input is an array of 1, 2, 3, 4. The actual output will be probabilities of 3 values. So this example says there might be a 0.3% probability that particular input belongs to class 1, 0.2% probability it belongs to class 2, 0.5% of probability it belongs to class 3. And since 0.5 is maximum, it will eventually return an array of 0, 0, 1, saying it belongs to class 3. And the attackers use this label to train their models. And their standard assumption is 0, 0, 1, or the final output is equal to the probabilities of each class. They miss out this 0.3 and 0.2 probabilities, and they assume it to be 0. So that's where the attackers lack in duplicating these models or steal the models properly. It will take so much of time and resources for them to reach to the final efficient model. Yeah, so just take a look at this table. This explains how much the attackers are losing. Let's see, the actual output in the first value is 0.2, 0.3, 0.5. There's no doubt the first label belongs to class 2, but they are missing the loss of 0.5. When the attackers train their models, it would be easier and it would be efficient to duplicate the model when they are having the probability values of each and every class. With the current attack methodology, the attackers are using cloud API output. So they'll take these values and they are losing this much critical information which is used to train their model. So we try to overcome this unconventional probability loss and we try to make it better. So there are few things there are few areas where we can improve and fasten this attack, and we could be able to clone the model or steal the model quickly. So first thing is reconsider the way we analyze the labels. Just as I explained before, having the access to all the probabilities 0.2, 0.3, 0.5 instead of the binary outputs, they will help us to train the model quicker, and the optimization function will be able to assign the weights properly. Followed by learning parameters in hyperspace. So you could just read that point. It says we have to learn the boundaries perfectly. What does that mean? It means this is never equal. You see the assumption part? So we have to make sure our model is nearby to this the probability values. Let's say your output is 0.3, 0.2, 0.5, or it is 0.1, 0.1 and 0.8. Both of them say it belongs to class 2, but one is 0.5 and another one is 0.8. They are having a huge difference, and we have to make sure our model produces an output which is equal to the probability values of these. Even though if our model is able to predict the correct exact class, it doesn't mean your model is accurate or it's perfect. To find the exact accuracy, we should try to compare the actual probability values of each class with your model. So that's one point. Followed by considering the probability of predicted class as 1 and others to be 0 will cause unwanted loss, which I already explained over here. And eventually, as he explained before in the optimization part, we will update the weights based on the current gradient values. This is the equation for that. So we just multiply the cost function with the learning rate. As of now, all the attackers and the attack methodologies focus only on optimizing the cost function. They mostly prefer to keep the learning rate as constant while they're stealing the models from the cloud. So we felt there might be a scope to improve the attack methodology and reach the optimal values in less number of time if we make some modifications to this. So yeah, this is our proposed approach, and Nikhil will continue with here.
Yeah, thanks, Rewanth. Okay, so you can see in this equation that the values of gradient is increasing because of the unconventional probability loss that we were getting before. So where can we actually overcome that loss? So you can see the alpha parameter there, which is called learning rate, which is being multiplied with the gradient that we are getting. So if the gradient is increasing, what we can do is we can decrease the alpha so that the weights won't change that abruptly as before. So once we change the learning rate based on our gradients, so this is the assumption that we are taking, that we change the learning rate based on our gradients to train our model and duplicate the target model faster. So yeah, this is why we call it GDALR, which stands for gradient driven adaptive learning rate. So based on gradients, we are adapting the learning rate in every iteration of learning to change the weights. So these three equations, we propose these three equations to the previous gradient descent methodology. So firstly, we take the gradient, which is represented by G here. So we take the gradient and then pass it to a tanh function. The tanh function actually converts your gradient to a value between range 0 to 1. 1 to -1. So the only purpose of tanh here is to convert the values in a particular range so that we can work on that range to get an essence of gradient and change the learning rate with respect to gradient. So the fact I function actually calculates the factor that we want to multiply the learning rate with. So we calculate the factor and we get a new learning rate called L dash. So here you can see when the gradient increases, the factor automatically decrease and the learning rate will also decrease. So the new learning rate will be in a range between your previous learning rate and 0. So it will be either minimum than the either less than the previous learning rate, or it will be equal to the previous learning rate. So we have tested this theory. Here you can see the gradient GDLR in action. The G dash value is increasing and the factor is actually decreasing. So there are two ranges. One is from -1 to 0 and 0 to 1, because gradient can be in a negative, and gradient can have a negative and positive value, which basically tells you where the slope is, if it's in the right side or the left side. So to test our algorithm, we have created three different classifiers. We have used three different classifiers and we have trained these classifiers on different data sets and gotten black box access to those trained models. And we run the GDLR with the traditional approach and compared the results of our attack. So there are basically three classifiers that we have used. One is logistic regression, another is multi-layer perceptron, and the third one is convolutional neural nets that we have seen before. So this is just an idea how logistic regression works. It is classifying the dots that are on y equal to 0 and y equal to 1. So y equal to 0 means it belongs to label 0, and if y equal to 1 means it belongs to class 1. So that is the equation, and logistic regression can be used for classification this way. So here you can see that the green line actually represents the proposed attack, the GDALR method, and the orange or yellow line will represent the traditional method, traditional machine learning model stealing method. On the y-axis, we have loss, which was the C that we have seen previously. So the minimum the loss means the model is being trained, and it will predict the output that you want it to predict. So the T loss is the loss attained by traditional method, and P loss is the loss attained by our method. So you can see the P loss is significantly lower than the T loss here. So in equal number of epochs, means in equal number of iterations, our methodology can actually train and steal the model efficiently. So this is about linear regression, and on the top there is L value, which actually means the learning rate. So we have tested it on multiple learning rates. We have also published this paper in IEEE, so you can go and check it, check the different methods that we have used to analyze our attack. So using MLP multi-level perceptron classification algorithm, we have trained the MLP on liver disease dataset. So it's a binary classification thing. So here you can see that the green line is very underneath the yellow line. So P loss is again actually very less than the T loss, which is around 100 times better than the traditional algorithm. So then we have trained convolutional neural networks on Landsat dataset. So this Landsat dataset had different images taken by satellites of Earth, and we have to classify the images to a certain type of terrain that it belongs to. So let's say there is tundra terrain. So it has some green pixel values, and let's say it has, we are looking at some desert, so the image will be different. So we have to take in those images and classify those images to different type of terrains. So we have trained CNN, the convolutional neural network, on this data set and try to attack the trained model using our methodology. So here you can see the results are exceptionally better because there are more number of classes than the previous one. Currently, people develop the models to classify multiple classes at the same time. So what we have seen here was there were 10 classes in handwritten digit dataset classification. There's a dataset called ImageNet. So there are thousands of classes in ImageNet. So more the number of classes, we get more unconventional probability loss, and which works in the favor of GDLR to actually train these models. So here you can see the results are exceptionally good than the traditional method. So our proposed method is giving 100 times better results. That means attacker needs 100 times less resources to actually steal the models, and less number of iterations also. So are there any mitigations to these kind of model stealing attacks? Basically, there are no mitigations. People are currently working on finding out the mitigations to these attacks. So there is one method proposed is to perturb the output of cloud APIs. So if you are getting something like 0.2, 0.1 and 0.3 as the output of cloud API, then we can change those values and tweak those values in a way that attacker won't be able to train his own models based on those values. But here we are only considering the final class of our model, final class of the cloud API predictions. So this mitigation will actually not work on the GDLR methodology. There are few papers that are trying to predict where the attack is happening or not, which is again like a cat and dog game. So you check the queries that are coming to the model and try to predict whether an attacker is actually trying to steal the model or not. So these are all the mitigations, and it actually opens a wide area in machine learning security. As previously there were adversarial learning attacks, and now there are model stealing attacks, and there are many more vulnerabilities that are there in how machine learning models are developed and deployed and have given access to the users. So this actually opens a wide area of research, and people are taking currently interest in that and working on it. So this is it for the talk. Do you have any questions?
Are there any questions? Then I would like you all to give a big hand to Rewanth, and Nikhil, Joshi.
Thank you.